Yeah, unfortunately, I made it.
Yes, is it okay now? Yes, it's okay, perfect.
Right, so hello everyone. Today I'll be talking about the Industrial Ontology Foundry core ontology. And before we dive into the core ontology, well, just as a bit of a background, what's the motivation behind IOF anyways? And that is the representation of data in a consistent manner across all manufacturing domains. And we plan to achieve that by creating a suite, an ontological suite that consists of open source ontologies that are mutually consistent and hence can be utilized together to represent the manufacturing domain, both on the data and the knowledge level. And this idea is nothing new. It essentially is inspired from a similar effort that occurred in the biological community, more specifically the biomedical community, namely the OBO Foundry that already demonstrated the benefits of this approach. As for the suite itself and how it's structured, we are actually using a tiered architecture for our ontologies. As we see in the basis, we have a foundation ontology, while at the top we have the application ontologies. So the idea is to go from a more abstract level to a more specific level systematically. If we look at what's the domain of the IOF actually, first we see the mid-level ontologies where the core belongs. The idea is to represent concepts that are common across different manufacturing domains. And from the core and some other domain-independent ontologies, such as, for example, a measurement ontology or daytime ontologies, we built domain-specific ontologies, which can then further be extended to the subdomain or the application level. Now, as for the foundation ontology itself, we have chosen BFO. The question is, why choose BFO among all the top-level ontologies? And the main points are that it's compact, it's well-maintained, and that it has a large user base, and also that it has already been used in the industrial domain, as well as demonstrated its value in the biological domain with a lot of disparate data sources. As for the actual bit of history, how the IOF core got developed, first, a lot of submissions were analyzed that contained terms that were submitted by a wide array of manufacturing experts. Then a careful analysis was done to essentially determine which terms are most cited, so in other words, most utilized across in the entire manufacturing domain. Then those terms, which were around 20 of them, were further refined and formalized by collaborative work of both domain and subject matter experts. And finally, gaps in the sense to better define those terms were identified. So new terms had to be introduced, and also a lot of working group chairs, which represent the domain reference ontologies, requested to include certain terms so that the IOF core can truly be a basis for their domain-specific ontology. After going through several internal review cycles, we got to the release stage of the beta version. And to get there, there was actually a vote by the working group chairs, which determined if it was ready for the beta release or not. And I've listed here a lot of criteria that were considered for the release, but I think the most important ones were that the terms are broad in scope, non-redundant, that they can be understood by subject matter experts, and that they're also, both in the definitional and the axiomatic sense, coherent with the understanding of the term in the domain of question. And of course, the ontology was ran through the Hermit reasoner to ensure that it's not logically inconsistent in any way. As for the summary, the core has 57 classes, 20 are defined, 37 are primitive, and out of them, 8 are purely primitive, which means that there is only simple inheritance. On the property side, there are 38 properties, and what these summary statistics actually demonstrate is that we tried to axiomatize core a lot, and that we also emphasize reusing properties instead of introducing new ones. Now here's a picture how the IOF core actually aligns with BFO. Let's split it into two pieces just so that it can actually be seen. And here we have the occurrent and the GDC branch. And I would like to highlight main classes, and that is from the occurrent side, the plan process, state, process, characteristic, and event. While from the GDC side, there is the information content entity that got extended with a lot of identification and specification classes. As for the material entity branch and the SDC branch, we defined a lot of classes that are connected to the actual life cycle of various entities, as well as extended object and object aggregate to material, artifact, person, system, and group of agents. While we also did a lot of work to introduce new roles to adequately model the industrial domain. Now I'm going to go into details about some of these classes. First of all, I'm going to start with information content entity, which is a generically dependent continuant that is about some entity, or in a more user-friendly manner, information specification, pattern, thought, or idea that's independent from its physical media. So this definition choice actually has two consequences. One is across different bearers, you can identify a piece of information as the same as long as its content is unchanged. And also, the is about relationships actually allows us to draw a clear distinction of what a piece of information is and what it actually references. So as just a small toy example here, if we have, for example, a temperature recording from some sensor, we can clearly see that it is about temperature. And also here, through the relationships, I demonstrated essentially that it can have multiple bearers over its existence without its essence being changed in any way, or in other words, by being a single individual. But the about relationship is really, really generic. We usually need to know the context, how a piece of information references an entity. So we introduce three subspecializations, that is prescribes, designates, and describes. Prescribes is used as a rule or a guide in the case of things that unfold in time, so in other words, occurrence, or as a models the things that persist to time, or in other words, continuance. Designates uniquely identified entities. By uniquely, that means there is some certain context in which it identifies the entity, and one information content entity can identify exactly one entity. And finally, there is describes that characterizes the entity in question. The property prescribes was really utilized a lot in core to define a lot of specifications that are important for the industrial domain, which are summarized here. And those are briefly actions, objectives, plans, designs, and requirements. For the sake of time, I'm not going to go through all of them, but it's worth mentioning one peculiarity, and that is the difference between a design specification and a plan specification. So a design specification prescribes something man-made. Something man-made can be both real or digital. It can be a simple object or a complex system, but it does not prescribe a process. So it does not actually tell us how something is built, and which is why it is axiomatically constrained through the only to prescribes only continuant. On the other hand, the plan specification actually prescribes how a process should unfold, or more specifically, a process should have clearly defined objectives and a set of actions that are needed to achieve those objectives. Now, to move on from digital or the information side to more the representation of real-world artifacts and the extension of object and object aggregate, I would like to point out the material artifact as an object that is deliberately created to have a certain function. Now, what do we mean deliberately created to have a certain function? Essentially, that its function is not a result from some evolution or some spontaneous action, that is actually prescribed by a given design specification. So it's clearly engineered. On the other side, for the object aggregate branch, which is essentially how objects can be aggregated and combined together, we have a system, which is a collection of elements that are in interaction, as well as a group of agents, which is essentially a grouping of agents that consists of only agents. And just to make it more clear for some of their subspecializations, there's engineered system, as well as an organized group of agents. Engineered system, yet again, the main point is that it is designed, while for the organized group of agents, yet again, that there is some prescriptive information telling why are the agents grouped together and what do they tend to achieve together. As I mentioned briefly, Another important thing is to actually represent life cycle phases of entities, and this is a quick toy example, which is material entity that is produced by one manufacturer and sold to another, is utilized by that different manufacturer as a raw material. The problem here is that the material itself doesn't change, or in other words, its identities and properties, but its utilization is completely different. So to solve this problem, we actually came up with as strategies is to introduce various roles and corresponding defined classes for these roles, which are defined through the has role property. And here we see those classes, and that is agent, maintainable material item, material component, product, resource, and raw material. For the specific use case in question that I mentioned, we can see here that this material entity was produced in some product production process. It, at some point in time, acquired material product role. This role was realized when it was actually bought by the other manufacturer. At a later point in time, it acquired the raw material role, which was then realized in a manufacturing process. So we actually can see here that we can understand the context, how it's utilized, and for how long it should be considered as such. Now, to actually explain what we mean by role, taking from BFO, role is an externally grounded realizable entity. What does that mean? Well, the role can cease to exist even though the physical barrier is not changed. So it's external, it's not based on some physical property of the bearer, and being realizable that it's only exhibited in specific circumstances. So from that point, what the IF tried to do is devise some sort of pattern how we want the roles to be defined. And we determined that we want to define them in a way that primarily indicates the context in which a material entity exhibits a particular role. As examples, the material product role is exhibited in sales, buying, or supplying, while the material component is exhibited when material is a part or planned to be a proper part of another material entity. So for some roles that are really crucial to our ontology, it's the agent role, which is a role that something or someone has when they act on behalf of a person, engineered system, or group of agents. Acting on behalf of essentially means that it participates in some process and performs some actions to achieve the objective set by the person, engineered system, or a group of agents. So this definition has several implications, and that is, it has the ability to autonomously perform actions. Those actions are performed to achieve the objectives. Also, what is not clear from here, but it is part of the entire process, is that acting on behalf of oneself is allowed, but on the other hand, entities that are chemical or biological in nature are not considered agents and will be treated separately at a later stage. Another clarification is the difference between a material resource and a raw material. So a material resource is a role played by a material entity when it is available to a person or group of agents or engineered system. The availability means that it has some internally grounded characteristics, so a disposition that the agent actually needs to achieve a certain objective that the agent carries. So this can actually help pinpoint all the material entities that the agent can use or is using at the moment. While the raw material role is more specific, it's actually held by a material entity when it's acquired by a business organization with the plan to be transformed or modified in a product production process. So it's only limited to externally acquired material entities and also to those material entities that are going to be consumed or modified in a product production process. Planned process is the main point of the occurrent class, and that is a process that is prescribed by a plan specification. For the sake of time, as I already went through this with plan specification, it encompasses a wide array of processes, and that is things such as manufacturing, computing, location change, measurement, and business processes. But not all activities are planned. So the BFO introduced several other current classes. There is state, which is represented as a process where the attributes of participants remain constant or within specified ranges. So state must have a duration, It must be a state of a material entity, and on the other hand, the specified ranges does not impose any constraint how narrow those ranges need to be. We also have event, that is an occurrence that is recognized by an agent and typically recorded. So that means that we can account for both instantaneous and durational events, but we do impose a constraint that the event has to be identified, although this does not have to temporally coincide with the event itself. And finally, there is a process characteristic, and the main driving use case behind it is to represent rates, but it's essentially an attribute of a process, and it's intended to be extended and refined in the future to be the counterpart of the SDC branch for the continuance. And finally, the areas that need to be addressed in the immediate future, as you can see from my talk so far, there was a lot of words containing material, material, material. So in other words, for a beta release, we focus primarily on the physical world, while the digital artifacts still need to be, patterns for them still need to be defined and also refined. And they will specifically focus on their actual representation, their connection to hardware, and what their life cycle is. Also, measurements need to be further analyzed and defined in terms of what units of measurements, how to utilize units of measurements, should we use an external ontology or devise our own, what is the actual scope of measurements, how measurement provenance is handled, and so forth. Process characteristic is currently really underdefined, and its scope needs to be better formalized. Also, how a process characteristic depends on entities participating in the process needs to be elucidated. And finally, with the advent of digital twins, essentially patterns that can help with the data representation related to digital twins need to be developed. And I would just like to thank everyone from the IOF community for their amazing contributions over the years.
Thank you very much. Okay, so is there any question? Yes, thank you for this presentation that is very clear and full of facts and clearly show us what you mean. I have a question, but this is because of my lack of knowledge in this area. When you use a material, it's for a certain purpose, but you don't always measure its property. It has a certain performance that you can describe or feel. Is this aspect of the material taken into account into your description?
Yes, absolutely. Absolutely. You can, it's really, really flexible with respect to that.
Thank you. Any other question? Yes.
Not so much a question, but a couple of comments which are good to have a response to. You mentioned measurements, and there was a workshop last year, I think, it was certainly during COVID, by the BIPM about the International Vocabulary for Metrology came up because it's essentially it's the Bible for metrology, but is in fact extremely difficult to understand. And it was recognized that taking the Vim, making the Vim more formal was one of the challenges, which I think we have as ontologists. So I think that's a major thing, because initial work such as QUDT has really only scratched the surface. There's a lot of details from the formal metrologists. What a unit of measure actually means at a great philosophical level. Is it, it's a particular phenomenon which you extract something from. So that seems to be some work to be done. And the other thing which, again, I would like is essentially just a comment that the IOF core has a parallel in ISO in the core vocabulary for industrial data, and Evan Wallace of NIST, I think, is involved in both communities, and certainly we see harmonizing there and maybe making sure that ISO and IOF are at the same in terms of the glossary only as the first stage. That seems to be an extremely important next step.
Thank you. And I'm really glad that you mentioned all those aspects because we're actually working on them as we speak, especially with respect to the vocabulary of mereology and how to actually formalize it. So thank you very much for your comments.
Thank you. Any other question? Yes.
Thank you for explanations. It was very clear. But one thing that I would like to ask to you is that how you ingest existing ontologies. I mean, we all know that nowadays each organization outputs their own standards. So for one thing, there are so many standards existing. So what is the process of evaluating which one is good to take and to be sure that there is no redundancy within your within ontology? Thank you.
So that's actually a great question, and that's actually the main motivation behind the existence of the IOF is that there are many standards, many specifications without any actual connections between them. So that is why we sort of developed our own independent ecosystems, but for everything that's related to standards, we actually utilize them as our inspiration for the core. And as for your question, how a specific standard is compliant or non-compliant, well, its terms and how it actually represents those terms need to be compliant with multiple domains and be actually compliant with our ontologies.
Yeah, because the risk is that you output another standard again and
Of course. You're absolutely right, which is why we're trying to reuse existing definitions and standards as much as possible. But we cannot guarantee that each standard will properly map to our ontologies, of course.
Thank you.
Perfect. Another question?
Thank you also from my side for this interesting presentation. I got a good impression of what the IOF core is about. And my feeling is still that it's rather abstract. So when you say it's for the manufacturing domain, and like having a basic knowledge about the manufacturing domain, I could imagine all these patterns to be applied. My question is, like, what did you make to make these decisions? So what was your guidance to include exactly those notions and concepts and patterns, and not others? Like earlier, Walter presented a work where they used competency questions as a guidance. Did you do something similar, or how do you?
So yeah, there were several use cases that were submitted that demonstrate the value of an ontology, but the main guideline for selecting the term set that we have is these submissions that I have been talking about. So there were over 600 terms that were actually sent to the IF core community, and the idea was actually to find which are the most abstract, as you mentioned, that can cover the broadest basis possible in our domain of question, so that more specific domain groups can build upon them and refine those terms.
Okay, thank you.
Thank you, Miloš. So now we will move to the last presentation in this session. It will be an online presentation by Pierluigi Del Nostro. The paper is the Cameo Ontology, Exploiting EMO Multi-Perspective Versatility for Capturing Materials Characterization. So here, presentation about materials. So I don't know if Pierluigi is online.
I'm going to open a new session.